I'm a project engineer with the City of Saskatoon Environmental Services branch. We've been involved with various energy projects throughout the city, ways of cutting back on our utility bills, finding efficiencies, and then reducing our greenhouse gas emissions. So today's presentation I'll be focusing on some of our energy management initiatives that we've got set up. So first, just a little bit of background. We're members of what we call the Partners in Climate Protection. We joined this group in 2004. It's a group committed to taking action against climate change. In PCP, this network, there's about 120 Canadian municipalities. And municipalities are our main target because, going by what the PCP's released, they feel that half of Canada's greenhouse gas emissions are under the direct or indirect control of municipalities. So that's either like in our civic facilities themselves, how we manage the business of running the municipality, as well as our policies that we pass on to the public and the services we provide to the public, how that all influences. So for us, we've done a corporate inventory about what's in our direct control of what produces greenhouse gases. And you can see right off, one of the main ones, water and sewage. That's primarily from the pumps that it takes to circulate the water, some of the water treatment process, the wastewater treatment process, the electrical demands and such. We've got an initiative there to cut that back by replacing all of our old pumps. Like, they have some major pumps in the water treatment and distribution facility. If you know anything about pumps, 1% of the actual cost in operating is the actual purchasing of it, and like 99% of the costs are the operation. So there's a definite benefit to putting in something newer and more efficient there, just the operating costs as well as the benefits to the greenhouse gas emissions. Streetlights throughout the city. Streetlights are run and operated by Saskatoon Light and Power. So the initiatives there are, of course, we're going to need lights, and as we expand the city, that's going to grow and grow. So the point is, how can we get the most lights out of the least infrastructure? Like, how can we spread them out? What can we do for physical design of the head to direct the light where it's necessary and having less waste light? And also light technology. There's more and more push going towards, or research going to LED lighting, which is a little bit more energy efficient. We're still working on like some pilot projects to see how it actually works for the city infrastructure, but that seems to be one of the main directives. Vehicle fleet, getting more efficient vehicles, how we manage the fleet, how we deliver things like our bus services, how we do the routing, garbage collection, how we do that. Like, there are things that we can do in efficiencies of the system as well as the vehicles themselves to try to cut back on that. The last big block, buildings, and that seems to be the biggest contributor, and that one's the one that's a little bit harder to grasp. Well, what can we do to get the building portion under control? And that's what's kind of fallen on our department, environmental services, to come about. What kind of initiatives can we do to promote more energy efficient buildings? So our first reaction was we hired an energy management project engineer. His name's Chris Richards. And the whole presentation that I'm giving tonight will be based on his works within environmental services. He was unavailable tonight, so that's why I'm filling in for him. Chris is a PN. He's got a Master's of Science. He's a certified energy manager, and he's a lead AP. So his education is mechanical engineering. His master's was done under Rob Dumont, who was a major contributor or technical aid on this building. And he used to work with Integrated Design, which is a consulting company for making energy efficient buildings, doing energy management services, such things. So he comes with a lot of good direct experience. One of his first projects is the ACT Arena. And here we're looking at controls and monitoring. This is a Sask Power pilot project. So there's the ACT Arena, which is in Sutherland. So Saskatoon is participating in a pilot project for Sask Power. And it's basically using controls to save energy in this arena. Now, if you know much about Sask Power, they're kind of at their maximum generating capacity. They're basically using all the electricity they can generate. With the province growing as much as it is, it's going to be a major cost to build that next power plant to supply our needs. So Sask Power's got a lot of initiatives to do what they can to kind of cut back on the demand, to get them through those next few years until they can get more generating capacity. So this initiative is based on, if you think, well, how many skating rinks, hockey arenas, curling rinks are there throughout the province?
1,002.
So if we can do things to make them more energy efficient, to reduce our electrical demands, that's a big bonus for their demand cycle. And like the other side of that is, well, the more electricity that you save, the less you have to produce, which means the less greenhouse gases you're emitting. So this particular deal, actually, we've got a really nice one with SaskPower. They're putting all the money up front. They're buying the equipment, they paid for the consultants, they're doing everything to get the infrastructure in place. We've agreed for them to monitor for a year, see what the savings are, and if the savings are tangible, we will purchase all the equipment and then we will expand the service throughout the other city arenas. And SaskPower then has the data that they can go and take around to the other rinks around the country. So the theory behind this is, if you think of an arena, you've got your outside temperature, which is cold in the middle of winter. You've got an airspace inside that you have to heat to make the inhabitants comfortable. As well, you have to maintain an ice sheet inside the arena. And these things are kind of fighting each other. So we're burning natural gas to heat the airspace, which is heating the surface of the ice. So we have to use electricity to cool off a brine to maintain the ice. So we're using energy two ways fighting each other. So is there something we can do to improve this situation? So if we look at the ACT arena, what we have been doing in the past is heating at about 14 degrees Celsius all day long, daytime, nighttime. And to maintain a good ice quality, we've had to keep the ice surface chilled to about -6 degrees Celsius. So that's a temperature difference of about 20 degrees Celsius between the air temperature and the ice temperature. Now this is going all day long. And the idea is, well, what would happen? Our first step was, well, what would happen if we just turn down the heat at night? Nobody's in there at 2 in the morning. Why are we heating it to 14 degrees? So right away we get a natural gas savings by not heating for those hours. Because the air is not as hot, we don't have to put so much energy into maintaining the ice. So the other side of that is we can let the ice get a little warmer. So we get our natural gas savings here, we get electrical savings there. And now we're dealing with a 10-degree temperature difference as opposed to the 20-degree. Now, a key part of this is actually to putting in proper controls. This is a thing that you don't want to leave to a manual operator operation, because they're inconsistent, getting the timings incorrect. An operator says, oh, that's way too warm, and he'll turn it down too cold, or they'll miss a date, they'll miss a point, and they'll leave it too warm too long. So it's important to have that as a fully automated process to get actually the best energy efficiency out of it.
So can I ask a question? Why are
Sure.
you stepping it down through the day?
Oh, okay. Let's see if I can just back this up.
Are you using PLCs? Programmable logic circuits?
I'm not exactly sure what they've got. It's just an on-off switch. Now, what the logic is behind it, I would assume that there's a PLC involved, but it is just it's not a very detailed control mechanism. It is a very simple thing. The reason why we step it down is because at first, there's something to do with the length of time the ice is exposed to that temperature, that you have to constantly get it colder. Like even if the air maintains the same temperature, you have to bring the ice temperature constantly down to maintain that good surface.
Oh, okay.
Plus, I think there might be something to do with the peak hours of usage.
I was going to say hours of usage probably.
So the more people skate on it, the more you've got the Zamboni flooding it, the colder it has to get, because it has to take that energy out of that water that you're putting across the rink all the time. So the next step is, if you think, well, right now we're heating this entire airspace, but the goal really, we only have to keep the people warm. We want this area warm. With one system heating the entire building, we're also heating above the ice sheet. But ideally, we'd like to actually keep that cooler. So part of this process is, now that we've got the controls in, we've got the monitoring in, we're going to watch for a year and see really, like from various different temperature readings across the building, different electrical readings, to see, is there really an opportunity savings here? Is the opportunity exist for us to save enough money to put in the infrastructure to have 2 heating systems, a separate heating system for the spectators and a separate heating system for above the ice? So as part of that, again, this is part of the SaskPower project, we've got an online monitoring system. So it's monitoring various different things, the amount of airflow in the facility,